Hello, today we want to talk about acid and bases. We've seen some acid and bases in general chemistry already. Acids like sulfuric acid, phosphoric acid, and nitric acids are used to make fertilizers. Nitric acid is also used to make explosives. Hydrochloric acid is found in gastric juice. Organic acid like citric acid are found in citrus fruits and are used in foods and drinks, as well as in cleaning agents and cosmetics. Acetic acid is used to make vinyl acetate, an important precursor for polyesters, and also as a 5% solution in form of vinegar. Formic acid, which is found in ants, is used to make antibacterial and preservative compounds. On the basic side, we have sodium hydroxide, which is used in the paper industry, in the food preparation, and in cleaning. Ammonia, the most important application is to make fertilizers, but is also used in many cleaning agents. Methylamine, which is a slightly derivatized ammonia, is used in pharmaceuticals and pesticides. So as we see, acid and bases have a very wide variety of usages. When we look at the strength of an acid, we first look at the electronegativity. We learned in general chemistry that electronegativity of the elements within a period increases from the left to the right and decreases from the top to the bottom of a group. What we see in this table is that parallel to that, the acidity of the compounds increases. Methane, which is considered a very, very weak acid with a pKa of 50, is a much weaker acid than ammonia, which is also not really considered an acid, and water. Hydrofluoric acid, on the other side, is a significantly stronger acid. It's still considered a weak acid in the big scheme of things, but we would consider this an acid. If we go to period number 3, we see a similar trend that silane is a very weak acid, phosphine is slightly stronger, hydrogen sulfide is a weak acid, and hydrogen chloride is a very strong acid, and this trend goes for period number 4 and period number 5 as well. Another thing we're going to see is that the more electronegative elements are present, the stronger the acid is. So hypochlorous acid is a weak acid, so is chlorous acid. Chloric acid, on the other side, is already considered a strong acid, and perchloric acid is also a very strong acid. We have more electronegative elements present, and together with this we have also more resonance structures, which we will see later on contribute to the stability of the conjugate base as well. In summary, the acid strength increases from the left to the right because the conjugate base is better stabilized by a more electronegative element. The second factor we're going to look at is atomic size, which is kind of opposing this electronegativity to some degree. We see that the atomic size decreases from the left to the right because of the stronger attraction of the electrons on the valence shell. That means the fluoride ion is much smaller than the methylite ion. If you go down the group, we see that the size of the conjugate base increases because as you go down the group, you have more and more electrons, you have more principal shells, and the size of the atom or the ion increases significantly. Parallel with the increase in size, we also see an increase in acidity, and this is largely due to the fact that the larger conjugate base is able to stabilize a negative charge better. The third factor we're going to look at is the charge. We know that the hydronium ion itself is a significantly stronger acid than the water, If you look at the example like carbonic acid, we see that the carbonic acid, which is a weak acid, is still significantly stronger than the hydrogen carbonate ion. The third example shows this for phosphoric acid. Phosphoric acid itself is a weak acid. If you're protonating the phosphoric acid, we actually end up with a strong acid, H4PO4+. On the other hand side, if we're removing protons and look at the dihydrogen phosphate and the hydrogen phosphate ion, those are significantly weaker acid than the phosphoric acid itself. Generally, we observe that positively charged acids are stronger because the conjugate base is a neutral molecule. And we also see that the more negative charge we have on the conjugate base, the less acidic the compound is going to be, because it gets increasingly more difficult to remove a proton from this acid then. The fourth factor we're going to look at is the hybridization. We see that the sp3 hybridized case, like an ammonium ion, we have a weak acid. The acidity increases a little bit if you look at the protonated amine, and ultimately if you look at the protonated nitrile, we see a relatively strong acid. The acidity also increases if you compare alkanes, alkenes and alkynes. While alkanes generally are very weak acids, alkenes are slightly more acidic. On the other hand side, alkynes are significantly more acidic compared to alkenes and alkanes. And we actually exploiting this when we do synthetic chemistry, because the terminal hydrogen atom can be removed by a certain basis like an amide or a hydride ion. The next factor we're looking at is inductive effect. In this case, we're looking at halogenated acetic acids. Acetic acid itself has a pKa value of 4.76. If we substitute one of the hydrogen atoms on the methyl group with a halogen atom, we do see an increase in acidity, and the more electronegative the element is, the stronger the effect is. If we replace two of them or three of them, we see the same effects in terms of increase of acidity, and the more halogens we have, the more acidic the compound is going to become. For example, trifluoroacetic acid has a pKa value of 0.23, which almost classifies as a strong acid. The next factor is resonance. If you compare the pKa value of phenol and cyclohexanol, phenol is a significantly stronger acid than cyclohexanol. The main reason is that in the case of cyclohexanol, we have a localized negative charge on the oxygen atom. In the case of phenol, we have resonance to consider, which helps to stabilize the conjugate base. And as we're going to see later, the more resonance structures we have, the more stable is the conjugate base, and the more acidic the compound usually will be. In the case of phenols, we can increase the acidity by introducing electron withdrawing groups, because this way we have also an inductive effect, which generally leads to an increase of acidity if these groups are placed in the para or ortho position. The effect is significantly less in the meta position. The next effect we're going to look at is the ortho effects. In this case, we look at substituted benzoic acid. Benzoic acid itself has a pKa value of 4.2. If you look at phthalic acid, we see a significant increase in the pKa to 2.94. We see a similar effect for salicylic acid and andronilic acid. The reason for the increase in acidity has to do with the stabilization of the anion. If you look at the hydrogen phthalate ion, we see that the remaining carboxylic acid group forms an intramolecular hydrogen bond with a carboxylate ion, which is formed after the first deprotonation step. And this leads to a significant stabilization of the negative charge here. If you look at the hydrogen phthalate ion from the side, we actually see that it's almost planar, and this indicates that these two carboxylic acid groups are hydrogen bonded. We see a similar effect in the case of the hydrogen salicylate. If you remove the hydrogen and the OH group stays behind here. In general, if you have the possibility to form an intramolecular hydrogen bond with the anion, we see increase in acidity because it helps to stabilize the anion. The next factor we're going to look at are some special cases for CH acidity. As we've seen before, many carbon-hydrogen functionalities are not very acidic. However, we can increase the acidity by introducing electron withdrawing group like a nitrile group, nitro group, or in this case an acetyl group. We see that in the case of acetonitrile, one nitrile group lowers the pKa value from 50 in methane to 25 in acetonitrile, which is quite significant. The effect is even stronger for a nitro group, where the pKa goes down to 10. For an acetyl group, we're going to reduce the pKa to about 19 if you introduce one group. If you increase two groups, the effect increases. In the case of malonitrile, we have a pKa value of 11, dinitromethane 3.6, and in the case of acetone, we add up with about 8. Then if you introduce a third one, we're going to see something which appears a little strange. For the tri-substituted one, the nitrile, we get a pKa of -5, which means this compound is actually a strong acid now. In the case of the nitro group, we still see somewhat an increase of acidity, but the increase is relatively small, and the same applies to the acetyl group. The reason for that is that in the normal cases we see a stabilization by the resonance. So in the case of the nitrile, we see a CN double bond and a nitrogen carries a negative charge. In the nitro group, we also see then the formation of the CN double bond, and then the two oxygens are negatively charged and nitrogen is positively charged. However, for this to work, we need to make sure that the lone pair and the acceptor group are in the same plane. The picture here shows the trinitro-methylite, and what we see here is that two of the nitro groups are in the same plane like the carbon atom, and the third one is somewhat perpendicular to this carbon atom, which means that it cannot really accept a lot of the electron density. So the key point is that an increased number of electron acceptor group increases the acidity. However, it is important that the electron withdrawing group, which helps by inductive and resonance effects, has to be in the same plane like the lone pair on the carbanion. If this is not the case, like in the trinitro compound or the triacetyl compound, the acidity is not significantly lower. The tricyanomethylated ion is actually planar, and that's why we see a significant drop in pKa value here compared to the trinitro and the triacetyl compound. Another thing we need to consider when we talk about acidity is the solvent effect. If you look at the two acids like acetic acid and hydrochloric acid, we have pKa values of 4.76 for acetic acid and -7 of hydrochloric acid in water. The pKa value increases for both of them if you go to methanol by roughly 5. However, if you go to apropic solvents like acetonitrile and DMSO, the acidity is greatly reduced for both compounds. In both cases, the hydrochloric acid is still the stronger acid, but it's also significantly weaker. The reason for that is generally that solvents with a high dielectric constant favoring the charge separation, and this is particularly true for polar protic solvents because they are able to solvate the conjugate base and the proton at the same time. In the case of the aprotic solvents, they're solvating the proton reasonably efficiently. However, the conjugate base is generally poorly solvated, and this leads to a significant decrease in acidity. If you look at base strengths, we can look at an example like ammonia, aniline, and acetate ion. We see that the ammonia is the strongest base, and aniline and the acetate ion are somewhat similar. In order to assess that, we're going to look at the pKa values of the conjugate acids, and this looks that the ammonium ion is the weakest acid and the acetic acid is the strongest acid of these three conjugate acids. As a result, we see that the strongest acid is associated with the weakest conjugate base and vice versa. This is a general trend. We can actually express this mathematically, that the pKb value of a base equals 14 minus the pKa value of the conjugate acid. Meaning, if the conjugate acid is a strong acid, the base is very weak, and vice versa. Let's look at a couple of examples. Arrange the following compounds according to increased acid strengths. 1 propanol, propanoic acid, and 1 propamine. Propamine is the weakest acid and propanoic acid is the strongest acid. How can we understand this? We've seen that nitrogen is less electronegative than oxygen, which means that the amide ion is less stable than the propoxide ion, resulting in a higher acidity for 1 propanol compared to 1 propamine. Propanoic acid has 2 oxygens, which makes it more acidic, and on top of that we also have a resonance effect in the propanoate ion. The second example, we're looking at 3-chloropropanol, 2-fluoropropanol, and 2,2-difluoropropanol. Again, which one is the weakest and which one is the strongest acid here? Trichloropropanol is the weakest acid and 2,2-difluoropropanol is the strongest acid. In all of these cases, we have a halogen atom presence. In the first case, 3-chloropropanol, the halogen atom is relatively far away from the anion, so it has an effect, but a relatively weak effect. In the case of 2,2-difluoropropanol, we have a more electronegative halogen atom present, and we have 2, and on top of this, the fluoroatoms are closer to the anion. As a result, they have a stronger effect in terms of stabilization. The next example looks at benzoic acids. We're comparing the acid strengths of benzoic acid, 4-nitrobenzoic acid, and 4-methoxybenzoic acid. 4-methoxybenzoic acid is the least acidic compound, and 4-nitrobenzoic acid is the most acidic compound. It turns out that the methoxy group is an electron donating group which increases the electron density in the benzene ring, which destabilizes the conjugate base. The nitro group, on the other hand side, is a strong electron withdrawing group, which reduces the electron density in the benzene ring, which facilitates the stabilization of the conjugate base, the 4-nitrobenzoate ion. Let's look at the base strengths of chloride, dimethylamide, hydroxide, and fluoride. The chloride ion is the weakest base because it's a conjugate base of the strongest acid, hydrochloric acid, followed by the fluoride ion, which is a hydrofluoric acid as the conjugate acid, which is considered a weak acid. Hydroxide is a conjugate base of ethanol, which is even weaker acid, and the dimethylamide is a conjugate base of a really weak acid, dimethylamine, which has a pKa value around 38. The last problem looks at the increased acidity of oxalic acid as compared to acetic acid. How can we explain the difference? In both cases we have carboxylic acid groups present. The main difference is that in the case of the oxalic acid we form an intramolecular hydrogen bond after the first deprotonation step. Like in the case of phthalic acid and salicylic acid we discussed earlier, the intramolecular hydrogen bond helps to stabilize the negative charge of the carboxylate group on the right hand side in this diagram. We form a 6-membered ring which is relatively stable. In summary, the strength of the acid is a function of the stability of the conjugate base. The better the conjugate base is stabilized, the stronger the acid usually will be. Factors like electronegativity, atomic size, charge, inductive effects, and resonance must be considered for the stabilization of the conjugate base, once they can have different strengths and different importance in a particular example. We also see that the stronger the acid is, the weaker its conjugate base is. For example, hydrochloric acid is a very strong acid. On the other hand side, the chloride ion is a very weak base. We also need to consider the solvents as a factor when it comes to the absolute acid strength, because it helps the stabilization by solvation. The better the solvent solvates the conjugate base or acid, the stronger the acid base character of the compound is going to be. The best way to get a good handle on the topic is to practice. If you see different examples, you learn to better evaluate which parameters have to be considered when it comes to the strength of an acid and the base. Thank you for watching, and until next time, stay safe out there.